The biggest shift this week is that AI systems are getting better at using supervision, data, and instructions in places where they used to break down. Tokenizer mismatches no longer block teacher-student distillation, pre-training data can be actively scheduled for speed and quality, and even zero-shot annotation is being shown to fail for a very specific reason. The model's internal priors can overpower your prompt. The common thread is control how much of a model's behavior you can actually steer and at what cost. Keep watching, because the real story here is where these systems still resist adaptation and where the bottlenecks finally start to move. Let's explore the first paper, Breaking the Tokenizer Barrier on Policy Distillation Across Model Families. Breaking the Tokenizer Barrier on Policy Distillation Across Model Families, a collaboration involving the Hong Kong University of Science and Technology and Tencent, shows how to extend on-policy distillation beyond shared vocabularies. The paper argues that standard OPD, used in systems such as Qwen3, MIMO, GLM5, and validated by Thinking Machines Lab, has been constrained by identical tokenizers, forcing weaker SFT-style cross-tokenizer transfer. Their solution is a dual-pointer chunk alignment algorithm, DPCA, that finds minimal, synchronized text chunks across student and teacher token streams, plus a semantic prior credit assignment rule that projects a teacher chunk's log likelihood back onto student tokens in closed form. In experiments with Qwen3, 8B as teacher and llama, 3, 1, 8B, SFT as student, OPD lifts the average benchmark score from 35.1 to 40.7 across AMY 2.4, AMY 2.5, AIM 2.6, Math 5.0.0, GPQA Diamond, and Live Code Bench, outperforming ALM and CDM. In a second setting, DeepSeek R1 to DeepSeek R1 Distill Qwen 7B, it raises the average from 48.8 to 52. The compute analysis is especially striking. To reach 44.4% on AIM 2.4, OPD needs only 20K additional training samples and 4.8 times 10, 19 flops versus 482K samples and 1.17 times 10, 21 flops for an SFT extrapolation, making OPD about 24.1 times more compute efficient. The key result is that Tokenizer mismatch no longer blocks dense token-level teacher supervision. Let's explore the second paper, Holistic Data Scheduler for LLM Pre-Training via Multi-Objective Reinforcement Learning. Holistic Data Scheduler for LLM Pre-Training via Multi-Objective Reinforcement Learning from Chenhao Dang, Jing Ma at Renmin University of China, and Mingjie Liao at Alibaba Group reframes online data mixing for LLM pre-training as a continuous control reinforcement learning problem and optimizes it with soft actor critic. The key novelty is a holistic reward that combines inter-domain gradient alignment, scheduled lexical diversity, and model stability. So the scheduler can favor data that is jointly useful, curriculum appropriate, and convergence stable instead of relying on a single loss signal. On the pile, HDS trains a Pythia 1B model for 50 billion tokens and reaches the same final validation perplexity as the prior best dynamic method with 44% fewer training iterations, while beating the static the pile weights baseline with 57% fewer iterations. At the end of training, it lowers validation perplexity by 13.6% versus TPW and improves MMLU by 7.2% on zero-shot accuracy and 4% on 5-shot accuracy over the prior best method. The paper also shows that the scheduler adds only 26 5M parameters and about 0.02 seconds per step, yet delivers a 2.21x wall clock speedup, and the gains persist at scale on Pythia 1-2B, where HDS reduces perplexity from 7.32 to 4.89 by the final checkpoint. Let's explore the third paper, on the limits of LLM, adaptability impact of model internalized priors on annotation task performance. This paper examines how model internalized priors constrain LLM annotation on toxicity detection, using 9 instruction-tuned models including OpenAI's GPT 4.0, Mini, Meta's Llama 3.1, 3.3, Mistral, DeepSeek v3, and Qwen 2B, 572B across 5 datasets spanning Twitter, OLED, GameTalks, Fox News, and Jigsaw. The central result is that definition-specific familiarity, DSF, semantic alignment between a model's own concept description and the task definition predicts zero-shot accuracy after controlling for dataset difficulty, with partial R equals plus 0.41 on an N equals 54 model dataset panel, while 3 memorization metrics, RAUG-L, BERT score, and embedding similarity, show no positive association. Prompting has limited corrective power. The overall rescue rate is only 34.8%, meaning nearly 2/3 of zero-shot errors persist even under aligned definitions, few-shot examples, and DSPy optimization. High-confidence errors are especially sticky, with rescue probability falling to 20.8% for confidence above 0.9. And confidence remains similarly high under misaligned definitions, exposing a calibration failure. Misaligned prompts can shift prediction bias by about 112.1% to plus 13.1%, depending on definition scope. Yet models stay overconfident rather than signaling uncertainty. The practical takeaway is that annotation quality depends more on definition alignment than on text memorization or model scale, and the paper recommends DSF-style checks before deployment. That's a wrap on today's AI paper highlights. Thanks for watching.